Okay, so yeah, this is section 6 and it's lab 3. So I have a few conceptual questions in here as well as a question where we're going to actually apply the clustering algorithms on a data set in R. I'm going to start with question 1 because this is the clustering problem where we're going to apply the algorithm, and then I'll come back to the conceptual questions afterward, just in the interest of time. So problem 1 is saying to download lab3_1.csv from campus. This is a data set for 12 fictional people. It includes their movie watching preferences. So imagine they've answered some survey data or provided some survey data. Each preference is indicated on a scale from 1 to 10 for 5 different movie genres. So lab3_1.csv, again, it's on campus, so you can download it there. I have it right here, the CSV file. And here's what it looks like. Okay, so we have our first column is the first name of the respondent, and then we have responses of values between 1 and 10 for these 5 genres in terms of how much they like it. 10 being I like it more, or 1 being I like it less. So we're going to try and cluster these 12 people. Okay. So once again, I've given the script. The lab script is pre-written for you on campus if you want to refer to it. I've also posted the lab solution that you can refer to. Again, I encourage you to try and, the script you probably want to have open to follow along with me. In terms of the conceptual questions, I would try to be answering them on your own rather than going straight to the solution file. So the solution script is lab3-script.r. It's again on campus. And it looks like this. Now, to get started, I'm loading a bunch of libraries here. I can briefly explain what each of these is for. They're not all super critical. The main ones that we're going to be using, actually, have I loaded all of them at the beginning? I think I may not have. Maybe it's a native function. So the clustering function is native. So RDSTK is the R data science toolkit. Not super critical that you have this. I'm going to show you, I'm going to be using this later for some geocoding and stuff to apply clustering to some addresses. It's just going to be a demonstration. Maps is mapping data. Well, actually, maps is mapping functions. Map data is data for maps. So like county boundaries in the US, stuff like that. ggplot I'm going to use to draw pictures. dplayer is a data manipulation package. So I showed you guys how to use a number of different tools in the first lab that are sort of native basic tools for manipulating data in R, right? Reading data in, adding columns, things like that. dplayer is more advanced methods that reduce the syntax. It makes it simpler to do a lot more things, essentially. So I'm going to show you some examples of how I'm using it in this script. I really encourage you to take a look at it. I could have a whole class just on this package if we really wanted to, but that would be more a data engineering class, okay? So I'm not going to. But I encourage you to take a look. There's tutorials online, and it's super useful. So first thing I'm doing is I'm reading that data set in, lab3_1.csv, using the read CSV file. If you happen to have your R script in the same folder as that data set, when you open the script, I can actually just request the file, and it will typically, unless you forcefully set your working directory to be something else, it'll look in the same folder right away for that file. Okay, you can also use file.choose here, right? Remember we had that function that I showed you, file.choose with parentheses, where if I use this instead of the string path, it'll open up a browser window and let me look for the file. Right, so I could do this instead. Right, if I call this, it opens up a browser window and I can go looking. Sessions 6, lab3_1. There it is. This will read the data fine, right? Yes.
The instructions, if it said like no such file dot or something, you said like reported like something.
No, in the virtual machine, if you're getting the error when you, so how are you getting that error? What are you doing when you run?
Like when I try to open the R script, like it appears like a message. And I remember like last time we did like something.
Yeah, actually, so it depends why you're getting the error. It might be that your shared folder is broken. If that's true, then you have to go to terminal and type vagrant reload in the big data box folder. If it's just that the file's not opening because R is throwing an error, close R with RStudio, reopen it, and open the file through this.
I tried doing that, it didn't work.
Okay.
So I'll have to do it.
So it may be that your shared folder is broken. If you don't want to fall behind, I suggest looking onto the person next to you, and then if it's still an issue at the end, I can try and help you. Okay. Yes.
I cannot go on the internet inside the virtual machine, so they always say like this site cannot be reached on any website.
Okay. Yeah. So again, if you're having that issue, look at the person next to you. I can try and help you afterwards, just because I can't. We'll run out of time.
Just a quick question.
Yeah.
The libraries, should we run them as well, or it's already good?
The libraries, you can run them.
Yeah, okay, if it's necessary.
Yeah.
we'll just
You can run them now if you want to run these commands, just to load them into memory.
Yeah.
If you don't have them installed, it'll prompt you to install them. Yes. If you get an error message, that means you haven't installed one of the packages.
I mean, I have the virtual machine. That's why.
Okay.
Right.
Yeah.
So it should be fine. You can check out one with me if you want to.
So, and by the way, just as a note of preparation, I would really encourage you to download the script, try running it ahead of time. You'll know if you're getting an error, and you can ask for help, right? Just going forward, that might be a good idea. So you can either use the file.choose argument, or you can use what I had here in the original script. You can give it the file path as a string. So I've read the CSV file into this variable, lab3data. I've given it this argument, strings as factors. So this means don't read a string variable as characters, read it as a factor variable, something like a nominal variable. Okay. So here's the data in the top right. We have our 12 observations. We have our variable names, and then the values. Okay. I can also double click or just single click this to view the contents. Here it is. It looks just like our spreadsheet. So first thing I'm going to do, I'm going to store the names column as a separate vector, because I'm going to get rid of it, because I can't cluster people based on their name. At least not, I could, but I'm not going to in this exercise. Okay.
Just very quick, because like for strings as factors you said false, so it actually like with this now, like that's why it's still reading.
It's going to read it as characters because I said, this is actually, you don't need this option. You could leave this out and we're not going to be working with factors or with strings in the exercise, so this is kind of an extraneous argument.
We remove the names column now anyway.
Yeah, we're moving it aside. We're going to bring it back for when we plot things, like clustering solutions and stuff. We want the people's real names to be there.
To assign them.
Yeah, so it's like an interpretable plot, but we're not going to use it in the actual clustering algorithm. So I'm taking the name column and putting it into a new vector called names. Okay. And then what I'm doing is I'm saying take the original data, everything except for the first column, overwrite it the same variable. So I'm basically throwing the first column away from the data frame. Right, so right now it's 6 variables. When I run this command, it's 5 variables. And the first column is now gone. Okay, so all I have left is numeric data. Okay, so the names are gone. Now, if I want to scale my data, okay, which I will want to in this case, right? Why do I need to scale my data?
To normalize it?
Right, but what's the main concern? What would happen if I didn't scale data?
Because I want to like be able to compare like the data points, like the distance. So having like the same measurement allows me to compare them across the different columns.
Right, I need a common range across all of my variables, otherwise I get into a problem where the things with naturally higher ranges drive the distance calculations. Right, they dominate the Euclidean distance, for instance. So actually the reason I said demo, this is how you would do it, is remember we don't need to in this case just because all the data is already measured on the same scale. Everything's from 1 to 10 already, so they already have a common range. So there's really no point in scaling. I could if I wanted to, but it doesn't matter in this case. Okay. If I did want to scale my data, this is how I call the scaling function. So the function's called scale. I pass it the data set. I have the option of what's called mean centering the value, so subtracting the mean value off of each variable. There's various situations where you might want to do that. It isn't so important here. And then this
Sorry,
is
can you repeat that? What center false?
center. If I say it's true, then it will mean center the variables. It'll subtract the average value off each column. Not important here. There are other reasons you might do that for other analyses. And then the last argument is a list. So it's the parameter is called scale, and I'm assigning it this list of values. This is the maximal value for each variable, right? Scale with respect to what maximum? 10, 10, 10, 10, 10 in this case, because they're all 10s. Now, you're going to have situations where you have a variable that doesn't really have a theoretical maximum, right? Like income, in theory, there's no upper bound on that. So it's not clear what you should scale relative to. Typically what you do is you'll scale relative to the biggest value in your data, potentially, or if there's something that's reasonable, right? Like it's going to be somewhat arbitrary as you start to think about this, right? But you make some choice about what the maximum is for the scaling process if there's no natural upper bound. Because I'm working with survey data, I know the maximum value is 10 because it can't be any bigger than 10. That's how the questions were written. Okay, so just to show you, I can run this. It stores the output in this. I put this demo variable here just for demonstrating what it looks like. Okay, and it's scaled everything to be between 0 and 1 now. Okay, I don't need to do it for this purpose because everything's already on the same range. So if I want to do hierarchical clustering, I need to pass it a distance matrix. So that means I have a matrix, an adjacency matrix, where every row is an ID number for an observation, as is every column. So I have 1 to 1, 1 to 2, 1 to 3, 1 to 4, and then I have 2 to 1, 2 to 2, 2 to 3, 2 to 4. And the cell of the matrix is how far apart are those two observations. That's called an adjacency matrix. So what I'm doing in the next step is I'm creating this matrix, right? So every row is an ID label for an observation. Every column is an ID label for an observation. And the cell where they intersect is the distance between them. I have to build that matrix and then pass it to the hierarchical clustering algorithm because it uses it in the algorithm, right, to figure out which things should be merged when. Yes?
Wait, but how was it again? Are we taking every observation and looking at the distance to every other observation?
Yes.
Every single other one?
Yes. It's a big matrix if you get a big data set. Yep. So so that's what I'm doing here. I'm creating that distance matrix. Okay. It's not actually going to, so remember it's a symmetrical matrix. So the lower triangle equals the upper triangle. 1 is the same distance from 2 as 2 is from 1. So I'm actually only calculating half that matrix, the lower triangle. So it's not as bad as it sounds. It's still bad. It gets intensive, but yeah. Yes?
That's what you just said is because like the distance, if I have like a triangle distance between like, let's say one point and the other is always like equal or lower than the distance between the other 2 points. Is that right?
No, actually, this is the reflection thing. So this is if the distance between A and B is equal to the distance between B and A.
Yeah.
So I only have to calculate A to B, and then I know the same is true for
Okay,
yeah.
so half the calculations only this.
Yeah. Exactly. So I'm creating the distance matrix, and I'm telling it what method to use, what distance calculation, use Euclidean. Okay, and this is the data to use in that calculation. Store the output in Euclid. Here it is. Okay, it's actually, so it is just a big matrix. Okay, let me try and make this. Okay. It doesn't show me the calculation for the distance between 1 and 1 either, obviously, because it will be always 0. Okay, so it just shows me the lower triangle. So this is the distance matrix, right? So from every data point to every other data point, I have this now, and I can pass it to the hierarchical clustering algorithm. Any questions so far? No. Okay. So the hierarchical clustering algorithm, it's this function, hclust. Okay. I'm telling it the distance calculations are based on this distance matrix that I just created. And then I'm telling it how to calculate the distance between clusters. Remember I had a bunch of those, right? Like average linkage and things like that. Ward's distance was one of those. Ward.d that's the name for Ward's distance for this algorithm. If you want to see how would I reference the other types of distance calculations, you can look at the help file for the hclust function. storing the output in this hierarchical variable. Okay, it's quite fast. Obviously, it's not a very big data set. So now I have hierarch here. Okay, this is essentially, it's an object with lots of different types of data in it. It's not like a data frame anymore. It's like a solution, a clustering solution, and it's got a bunch of parameters I can refer to that tells me things like, this is, for instance, what's going to be used to create my dendrogram, the plot, which I'm going to show you in a second. Okay, so I'm calling just a plot function, which is the native plot function in R. What I tell it to plot is that object I just created, hierarchical, and then I tell it what to use for the observation labels. Remember, I kept the names aside at the beginning for this purpose, so they could go into the plot at the end. Otherwise, it'll just show ID number 1, 2, 3, 4, 5, and it's hard to read. Okay. By default, the plot function tries to guess what should I do with this data given the data type. And it realizes this is a hierarchical object, right? So it's going to, or a hierarchical clustering object, so it tries to create a dendrogram. Let me just make my plot window big. Okay. So there's the dendrogram. So remember what I said. Ideally, what you want is a result where the number of clusters is fairly obvious. Won't always be this nice, but essentially a longer line means when the two clusters were merged, they were farther apart before that happened. So it may not have been a good idea to merge them, right? Shorter line means when we merge these two clusters together, they were pretty close together in terms of their centroids or whatever the distance measure I'm using, in this case, Ward's distance. So this is a good idea to merge these things together. They're probably part of the same cluster. So essentially, these ones all group together and they merge pretty quickly, so they were pretty close to each other in our 5-dimensional space of genre preferences. These two were close to each other, but kind of isolated from these others. So you might have 3 clusters here, right? So this group, these two, and then the remainder, or you could have 2 clusters. Again, it's somewhat subjective. It's up to you, right, to interpret the plot.
Why not 4?
What would the 4 be?
I mean, just like intuitively, like having Ken on one cluster, then having a cluster, but yeah, then you have one person, one cluster.
So remember, the clustering solutions, the 3 cluster solution is if I cut this tree where it goes with the line will cross 3 lines only. Right? So then we'll have 1, 2, and 3. The 4 cluster solution is going to be just barely above this line, but below that line, I think. It's
So
not
you
at all clear.
always cut it like at the same, let's say, point, like in
Here, I'll show you. So I'm going to ask this thing to give me the 3 cluster solution. Next. Rect.hclust, it's going to draw rectangles around the members of each cluster next, okay, on the plot in a second. So I'm saying take this object, give me the 3 cluster solution, and draw the rectangle in red. Okay, so that's my 3 cluster solution. If I wanted a 2 cluster solution, I could say k equals 2, and it will draw them. I wouldn't want to do it right now because it'll just draw them on top of the rectangles that are already there, right? But the 4 cluster solution won't be so obvious. Yes?
So you're choosing your feedback is you're doing that because
Yeah, this is purely subjective, that step. Yeah, I feel like it looks like 3 clusters make sense, but that's just I feel, okay? You may not agree with me. As long as when you're answering a question like this on the homework, you explain why you had that opinion. You reference some piece of evidence. That you'll be fine. You can disagree with me as long as you don't say 1 is the answer, right? That'll be bad. Okay. So that's how I can get the visual representation of the 3 cluster solution. I can also tell this thing, give me back the cluster assignments that go with that solution. That's what the cluster results variable is going to contain next. I use this cut tree function. So cut the tree such that there's a 3 cluster solution, and then give me the resulting membership back for each cluster, like which observations went with which cluster. Okay. So we have cluster results is here, and it's just a vector of 12 values, right? They take on values of 1, 2, or 3. So for observation 1, what cluster was it in? For observation 2, what cluster was it in? Okay? So now I have the cluster membership as a new vector, and I can add it back into my original data set, which is what I'm doing next with the column bind function, cbind. So stick the names column on the front again. Remember, we took it away at the beginning. We're putting it back. Then we have the data, and then we have another column, which is the cluster assignment. What didn't you like? Oh. Yeah, it gave me an error because I made my plot window small. It tried to refresh the plot. Okay, so now I have lab 3 hierarchical with 7 columns, and we see we have the name is back, the date is there, and then we have the membership. Okay? Now, if I want to figure out the centroid of these clusters, what is the centroid? It's the mean value of each variable among data points in the cluster. So it's supposed to be like the representative individual in this case, right? Their average preferences across genres. You could calculate that a few ways. You could subset the data set, right? So I could subset this new data frame based on the cluster result value. So I could subset it and say for cluster 1, give me the summary statistics, and it will show me the mean values. For cluster 2, what are the mean values? I could do that, right? What I'm doing here is slightly more, I don't know, it's quicker, right? I'm using the dplayer function here. If this is not apparent to you or it's not clear what the heck is going on, do not worry too much. I don't actually evaluate you on your understanding of this package. I'm just trying to introduce you to new functionality. So what I'm doing is I'm saying take this data frame, the one we just created. This is a percent, right arrow percent. This is called a pipe. I'm essentially saying take this and pass it to this next function I'm going to give you. It's input by default. It's the first argument that will go to the next function. So take this data frame and pass it to the group by function. This is a function that's part of the dplayer package. Group by what? The cluster results variable. So for each unique value of this variable, it's going to create subgroups. Okay? So it's basically doing subset, subset, subset. And then for each of those, right, it's going to iteratively pass each of those subsets to the next function, the summarize command. So it's going to automatically do all 3, 1, 2, 3, and spit out the results for each one for me. And I'm saying summarize what? So first, give me the mean value of action, the mean value of comedy, the mean value of drama. These are the names of the columns. It's going to spit back the mean values for each one within each subgroup.
It's just a more elegant way of doing this, what we could have done with like 3 or 4 commands.
Yeah, so it just simplifies the syntax and reduces it so you can do it all in one command instead of typing it all out. Okay, and there's your results. So cluster 1, cluster 2, cluster 3, we have the average value of action, the average value of comedy, the average value of drama. And it's truncated the others because my window was small, but I could store this output into a new variable. So I could call this lab 3 cluster centroids, right? So whatever the output of that command is I just ran, I can store it into a variable, like so. Here it is, 3 observations of 6 variables. Okay, so it's cluster 1, 2, and 3, the average value for each variable in each of the subgroups. Yeah. You're getting, that means, have you installed and loaded the dplayer package? So check that. Usually that means the package isn't in memory. Yeah. Okay. Yes.
I'm getting an error when you combine the names and the test results. It says arguments imply a different number of rows.
So this command.
Yeah, that one.
So if you look in the global environment window, check that the names column is here, right? So we need to check that, sorry, it's not there. It's here, has 12 values. Lab 3 data should have 12 observations, and cluster results should have 12 values. And if that's not true, something's gone wrong somewhere along the way. Is one of those not 12 values?
Let's say my name's
So you need to go back and run that names, this line 22. Yeah, so it's saying it couldn't find that vector. Any other questions? Okay. All right, so now I'm going to do the k-means algorithm. So the first thing I'm doing here, this looks a little bit more complicated. What I'm essentially going to do here, I need to make a call, remember, on what the value of k should be. Now, I'm going to show you how to do it in an automated way where you don't have to go through this process of plotting it and choosing eventually, right? Because there's this k-means function. Well, actually, do we have it? It's the library. No, I'm not going to do that. We are going to do this manually. This is helpful because it's good to understand exactly what's going on. So WSS, this is short for within sum of squares. So this is the cohesion value. Remember, within sum of squares, this is within a given cluster, the distance between each data point and its centroid, take the square of that value. Add all of those up for a cluster, that's the within sum of squares value for the cluster. Bigger value, the things are farther away from the middle. Right? Smaller value, they're closer together. We want this to be a small value. BSS is short for between sum of squares. So this is the distance between centroids of different clusters. I want, on average, all the clusters to be farther away from each other because that implies separation. So what I'm going to do, for every possible value of k, right, one cluster, well, you can't have a one cluster solution because that's not meaningful. That basically means you didn't do anything. K equals 2. Up to the number of data points in the data set. That's also not a meaningful solution because it means you didn't do anything. You're just treating each person as different, right? So there's no attempt to collapse rows if you use k equals the size of your data set. So generally you're going to go from 2 to at most size of your data set minus 1, right? Those are the feasible values of k you might think about evaluating, right? We never want to treat everything as one big cluster and we don't want all the data points to be their own cluster. Neither of those is useful to us. What I'm going to do, I'm running what's called a for loop here. Okay. This is a kind of a basic programming concept. Essentially what I'm saying is for each unique value in the brackets, so I'm saying create a variable I. We're going to start off with I being equal to 1. And then we're going to, for each value of I, we're going to do some things which are described in parentheses next. And then we're going to increment I to the next value. So I equals 2. Do this again for I equal 2. Do this again for I equal 3. So essentially we're iterating over the same code repeatedly. And I is representing, it's in some way it's representing what's the value of k. Okay? So I'm increasing the number of clusters and each time I'm trying out the clustering solution and storing the result. Try it again, store the result. Okay, that's what this code is doing. So what I'm doing here is I'm first creating a new vector called WSS, right? And it's empty to begin with. So C, remember, this is a comma list, comma delimited list. Repeat the value 0 how many times? The number of rows in my data minus 1. Okay. I'm actually going to evaluate a k of 1 here, despite that it's useless, but just for simplicity's sake. So create an empty list, which is essentially, it's as many rows as I have in my data minus 1, and there's nothing in those elements. It's just an empty list. I'm initializing the list, and I'm going to put the values in as I go along. Yeah, because we don't want to have k equal to the number of rows because then everybody's their own cluster and we don't care about that answer because it's not useful. Okay. Any questions about what I'm doing here? Conceptually, what I'm doing? Right, I'm basically creating an empty container with the number of slots is equal to all the possible values of k, and for each one I'm going to store within sum of squares when k was 1, within sum of squares when k was 2, and then I'm going to plot them and see where the values look the best. That's my k values. Okay. So create WSS is this empty vector here. It's got 11 values. They all start off as zeros. I haven't filled them in yet. Okay, and notice there are 11 values. 1 to n is 12, right? Because there's 12 people, so 12 minus 1 is 11. So I have 11 possible values of k I'm thinking about. Yes. Because if I say the length of my data set, that means I'm considering k from 1 up to 12. A k value, you can't have a k of 0. That means no clusters at all. This is going, no, because a k value of 0 is meaningless in k-means clustering. You have to have a k of at least 1. Right?
But still, when we have 12, why minus 1 to have 11?
Because a k of 12 is every data point, all 12 of them are in their own cluster. And that's, I could go to 12, I'm just saying it's not useful.
Ah, okay.
Right? There's nothing stopping me from going to 12.
Okay, and it's not going to be wrong when we go.
It's not wrong, it's just I don't care about it, because I
It's
wouldn't
like
use
with
it.
12 data points, so at least you want one data point to be
Yeah.
in another cluster with another data point. Right?
Yeah, you're assuming that you want to collapse data somehow.
Yeah, okay.
So a k of 1 means I'm collapsing everything into one cluster. A k of 12 means I'm not collapsing anything. I'm leaving them all as separate clusters. Okay? Yeah. Any other questions?
So you're saying that WS is to give us like 11 clusters.
It's going to give me the within sum of square value associated with 1 cluster, 2 clusters, 3 clusters, 4 clusters. I'm going to store those values in that vector.
Okay, but we're not telling that fine how many clusters we want to have.
No, so we're not running any clustering analysis yet. All we're doing is creating like an empty box where we're going to put the metrics associated with each cluster exercise in that box to keep track of it. Okay? And this is for the cohesion measure, so how tight were the clusters on average, and then this is for the separation measure, how far away were the clusters on average, for each unique value of k. Okay, so here's BSS has 11 empty slots, and then WSS has 11 empty slots. This is where I'm going to store those two metrics as I go along. So I'm saying, in this for loop, for I starting at 1, and remember it's going to increment up to the thing on the right side of the colon is the maximal value that I will take on. So from 1 up to the size of my data set, which is 12, minus 1. So from 1 to 11, starting with 1. First, get the k-means clustering solution for k equal to that value of I. So k equals 1 the first time. Call the k-means algorithm on my data, look for a clustering solution with k equal 1 cluster. Again, not useful, but I'm just going to do it just because why not? Okay. The clustering solution is going to be stored in here, k-means underscore temp. And k-means underscore temp is a clustering solution object. So it's got a bunch of metadata that describes the solution that I can reference. Two things I care about referencing here were what was the total within sum of squares? So the average cohesion essentially. Where it's not the average, it's adding up the sum of squares across all the clusters. Okay, so for k equals 1, get the solution, then pull out the within sum of squares value across all observations, and store that result in my empty vector I created before in the first slot. Similarly, pull out the cluster separation metric, store it in the first slot of my separation vector. Okay? I will increment to 2, and we're going to do it all again. Now k equals 2. And we're going to store, so we calculate k-means solution for k equals 2, pull out the within sum of squares value for that solution, store it in the second slot. Store out the separation value, store it in the second slot. K goes to 3. We do this repeatedly for increasing values of k, right, all the way up to 11, and then it's going to stop. And we'll have our two vectors are now populated with within sum of squares and between sum of squares values for each value of k. Okay, so you see here's your within sum of squares values are now all filled in, as are the between sum of squares values. Now, I'm going to plot these. I'm going to use these metrics over different values of k to see is there an easy way to choose what my k should be, right? Because I want to have a good balance between both of these two measures. This is also known as a scree plot. If you heard that term, this is what this means. Okay, so there, what I've called the plot function, I'm passing it the x-axis and the y-axis. That's the first two arguments. The x-axis is 1 to 11. Okay, it doesn't draw all the numbers there, but it's plotting 1 to 11 on the x-axis. And then the y-axis is what was the within sum of squares value. Okay, so for k equals 1, the first data point is our within sum of squares value. K equals 2, within sum of squares value. Okay. Color it blue. Type is what should the line look like. There's a few options there that you can look into with the help file. I could have made it a dashed line. I could have done some other things there. Yes?
So we should expect this kind of curve, because like the more case you have, the smaller.
Yeah. Yeah, and if we got all the way to 12, it would be 0. Yeah. which is again why that's not a useful number to consider, right? What I'm saying here is I'm setting an option that's saying the next time I call plot, do not create a new plot. Leave what's there and write on top of it. Okay, that's what this is saying. So essentially, par is short for, I don't actually remember, something about parameter, something like that, but basically saying I'm updating the plot is what this next option is saying, whatever I call next, not replacing it. You'll see down here, I'm gonna revert that change, so it goes back. So the next time I call plot after this is all done, it will create a new plot for me again. Essentially what I'm doing is I drew the first line, and now I'm gonna draw another line on top of it instead of replacing the plot altogether. So the next line I'm going to draw, again, the x-axis is the same. It's from 1 to 11. And the y-axis is now the between sum of squares value, so the separation result that I got across different values of k. Don't draw axes this time, because I've already got the axes there. If I draw them on top of each other, it can start to look ugly. Don't relabel the axes either, right? Otherwise, we'll start writing text on top of text. This time, make the line dark red. So blue is cohesion, red is separation. I want blue to be small, I want red to be high. Okay. So what I'm actually looking for here, I am not looking for the maximal value of between sum of squares in tandem with the minimal value of within sum of squares. That's true, that would be great, except what I'm getting then is not a clustering solution. Every data point is essentially by itself, because I'm going to have 0 for within sum of squares if I use k of 12, right? It's not plotted here, but that's what it would be. And my between sum of squares would also be quite high, the red value. But that's not a useful clustering solution. What you're trying to do with clustering is you're looking for the point where the line actually kinks, right? Where increasing the value of k doesn't give me that much benefit in terms of explaining the data. That's going to happen when it plateaus, right? So essentially it's like you're trying to get a balance between collapsing data. So essentially it's this balance between explaining everything that's going on, but also having a parsimonious model, like as simple as possible, but still capturing most of what's there. And you know that's kind of going on when you stop seeing much benefit. In some sense, as this thing goes up, that's the returns to increasing k. But you see the returns are diminishing, right? It slows down the benefits that you're getting as you make k go higher. So what you're looking for, it's again somewhat subjective, more art than science, right? But I'm looking for the point where this thing kinks. And as I increase k, I'm not getting that much benefit for giving myself essentially an incrementally more complex clustering solution. So you're looking for the elbow. It's called an elbow plot or a scree plot for that reason. You want the point where it stops, like where there's like a clear stopping in terms of the benefit you get as k goes up.
So basically, just to remember it again, like within sum of squares should be higher. I want that to be higher.
No, you want that to be low. That's the blue one.
Ah, that's the blue one. Yeah.
Yep.
Sorry.
That's cohesion.
Yeah. Okay. Like that's the cohesion measure, and I want the separation measure that's between the centroids, right?
Yeah.
And that obviously I want to be higher.
Yeah. So essentially what's going on, when k goes to 2, right, we get our measures improve a lot for adding another cluster. We go to 3, we add another cluster, and measures again improve a lot. They don't double, but almost in terms of their values in absolute terms. Then when we go to k equals 4, actually the improvement from doing that is kind of marginal. So it's like it's almost like it's again a subjective call, but essentially what you're seeing is complicating my clustering solution by adding a 4th cluster isn't giving me that much benefit in terms of capturing what's going on in the performance of the results.
Yeah, because you still have to treat like those data points in the separate clusters. So it would be
Yeah. So now you're going to essentially, it's like I'm going to have a 4th marketing program now, but I'm targeting people that really aren't worth targeting separately in some sense.
Like
Yeah.
more investment. In
Exactly. Okay. So you're looking for that kink. This is instead of using something like a silhouette width metric, right? What I'm doing here is I'm plotting both values separately instead of subtracting one from the other, right? I'm just plotting them separately from one another and kind of looking for a point where they simultaneously appear to do well. It's not always going to be the case that they're going to kink at the same spot, by the way, right?
I could also label the graph already that I see that, okay, red is WSS and
Blue is
blue
WSS.
is WSS and red is...
You can put, yeah, we're going to get the visualization of the last class. You can create a legend and you can do other things.
If I didn't know it from the code, I wouldn't be able to
Sure.
read much of it.
Yeah, yeah. We'll get to the last class, will be visualization, and we'll do like, how do you create a legend? And the plots are much more attractive than this thing.
Okay.
Any other questions? So from this, if I saw this, I could use this as evidence and say, looks to me like kinks at 3 on both metrics. I'd probably go with a k value of 3 as the right solution here. And it kind of lines up with the dendrogram too, so that's not that surprising. Okay. So if I want that solution, I can say, give me the cluster assignments. I'm going to store in segments. It's a new variable I'm creating, and I'm saying k-means with this data and use a k-value of 3, get that solution back, and store that results of the k-means algorithm in this new segments variable. And then this is, again, a k-means clustering object. It's the output of that algorithm. It has metadata, characteristics I can ask about. One of those is centers. This is the average value across all dimensions within each cluster. Right, so the segments object that came out of the k-means algorithm, I'm asking it, give me the centers result. So like that's the metadata that's part of the... Yeah, it's the centroid values. Yeah. Okay, and there they are. Okay. So this is the average response value within each cluster, according to the k-means solution for 3. So this is kind of like the representative individual in each cluster, what they feel like about these things.
So like, for example, the cluster 1, we see that they really don't like action and horror, but like really love comedy and drama.
Yeah, and they're kind of so-so on sci-fi, but they love comedies and dramas, as opposed to, this is kind of the person that doesn't, well, they like dramas, I guess, but they're kind of so-so on everything. They don't hate anything. Same with this one. This is really the only one that's really clearly separating out from other people and their preferences. They have strong opinions. This group tends to like most stuff.
But like for the third cluster, we see that they don't really like drama, so that's kind of like the separation.
Sure, compared to other people, they don't like,
drama.
yeah. So they're typified based on their preferences around drama. And these people are kind of middle of the road. They kind of like drama more than anybody else, but they're sort of middle of the road on everything. Okay. Again, it's also subjective how you would describe that cluster. Right? You have to give them a name. It's like that weird guy that was clustering women for dates, right? He came up with titles for them to help him like keep track about how he would interact with them or whatever. Okay. Okay. Now I'm going to get the silhouette width. So instead of just plotting these things separately, what I'm going to do is for a given clustering solution, I can draw the silhouette plot here. That function for that plot, it comes from the cluster package. So if you haven't installed it before, you'd need to install it. If you have installed it, then just using the library command will load it into memory. Here what I need is the square of the Euclidean distance matrix. Don't ask me why, but essentially remember we created that distance matrix earlier for the hierarchical clustering solution, right? Where the distance between every data point and every other data point in a big matrix based on Euclidean distance. So what this thing needs is you take the square of that matrix. Every value, you square it. Okay, and then you pass that as an argument to the silhouette function. So the first thing is it needs to know the cluster membership for each data point. Actually, yeah, so this is the cluster membership for each data point. Well, actually, it's the cluster solution. It's describing each cluster, so it's not entirely clear. Let me just show you what this is. Yeah, so it's the membership, the assignment of each data point to each cluster. And then the second argument is the squared Euclidean distance matrix, and that's going to be used to create the silhouette plot. So it's storing the output of this command in sil. The reason I'm not just plotting it directly is I want to put the names back in, so it's not using just ID 1, 2, 3, 4 on the plot. So I'm saying assign the names for those values to be the names that we originally took out of the data frame at the beginning, and then plot it. Okay, so here's our silhouette plot. There it is. Okay, so here's our average silhouette width. You could go through this process of increasing k, and instead of storing within sum of squares and between sum of squares, I could also calculate the silhouette value for that solution and store it. And I could plot what that looks like over different values of k.
See if I get maybe a more accurate result.
And this is the one where I'd care about just maximizing this value. Because it's jointly, well, you're still going to want the, actually, no, you're not going to just maximize that value. You're similarly looking for a kink where it stops improving significantly.
Exactly, like, could you explain again how to read this? So I see that for cluster 1, Cindy and Laura, we have 0.95, so 97. So we want that because it's a very high value, like 0 to 1.
Yes.
And then according to that, but
This is the average within cluster silhouette.
like the WSS.
No, this is the silhouette value. This is the average silhouette width within the cluster. So remember, silhouette width is the distance for each data point from the next nearest cluster centroid, right? That value, minus its distance from its own centroid.
Oh, okay.
So that's what each of these lines means. So as that number gets bigger, it means I'm either getting farther away from the next nearest cluster or I'm closer to my own center.
Exactly, like,
One or the other.
so the higher, exactly, like it's either
Bigger is
super
better.
far away or like also like super close to its own center.
Yeah. So bigger is better in general for these values. There's no number to look for that says now your solution's good. Again, it's all, I can compare solutions and say this solution's better than that one in terms of the average silhouette width, right? But it could all be garbage in the end. It might be that there's no good solution. Okay, any questions?
So we found that cluster 1 is more likely to like the genre action and drama.
Mm-hmm.
Now, find out which were the members that were in cluster 1. We've done something in the past.
So from the k-means algorithm, the way you get cluster membership back, it's this segments $ cluster. So this is giving you so for each user, which cluster are they in? And I could combine this with the original panel, right? And add another column which comes from here, which says what cluster membership am I? Okay, so I could know who's in which clusters. This also shows me in my silhouette plot I created, right? Which users are in which clusters. So I have the data. The way I choose to represent it, if I make a plot or a table or whatever it is, I can do that because the data's here.
So Cindy and Laura are the ones that are likely to be probably drama viewers.
They are, no, I don't think this is
Because
cluster
the silhouette
2.
plot doesn't tell us about that. No, about the product.
This first one, Cindy and Laura, are cluster 1, yeah. So they're the comedy drama lovers, who are pretty unique relative to everybody else, right? Because they have high preferences for those and they hate other stuff. Nobody else is really like that.
So for a smaller cluster.
Yeah, but that's why the silhouette width is so high. They're very different from everybody else in that respect. And if we went back to our dendrogram, here's Cindy and Laura down here. Okay, so this is Cindy and Laura. They're the two in that first cluster that are kind of different from everybody else, and they're on their own. They are the last two to be merged with anybody else, is the other thing, right? Like these ones all grouped together on the right before these two got lumped in. Yeah.
Very clearly again, so it was like the distance from one point to its next closest cluster is centroid
Yes.
and its own centroid, right?
Yeah, subtracting its distance from its own centroid.
To the other centroid.
Yeah. Okay, any other questions? Again, it's not always objective what the right answer is, but reference relevant evidence that you use to make your judgment, and I'm probably not going to mark you wrong for that, as long as your answer isn't crazy. Right? As long as you're not saying we should have 11 clusters here. That's clearly the right answer.
12.
That's definitely wrong, yeah. Okay, so that's the script. There's some other code here which shows you how to do some things in R that you could also do in Excel, or you could also do by hand for the next problems, the written ones. Okay, so in the solution document, you'll see I've written in red, a good answer would talk about this, and this, and this, right? And this is what the point breakdown would be. So you should make sure you're kind of following along with the lab solution when you do the homework and following the same steps, right? And giving the right answers. Okay. Problem 2. Consider the following data set which shows the results of 3 exams taken by 4 students. All scores are on a scale of 100. And I'm asking you to tell me which students are most similar to one another based on various distance metrics. Okay. So I've provided some code in R and a data set, which is basically just this data set in a spreadsheet, and shown you how you could use R to do all the distance calculations. You could also do them by hand, right? These are not extremely complicated ones, but basically what you need to come up with is a distance matrix. So you need to find out how far apart each person is from each other person using the different distance calculations. And then the question is which ones are most similar to each other depending on each distance metric. And so you're looking for the ones that have the smallest value in each case, right? Because they're going to be closest, smallest distance. So I guess I could do this now. So what I'm going to do, I've also got a solution where I've shown you how you can calculate this in Excel, by the way. In case you're comfortable in Excel and you know how to do VLOOKUPs and things like that, I've given an Excel spreadsheet that shows how I did the distance calculations that you can refer to if you're curious. I can show it here. If you don't know how to do VLOOKUPs and things in Excel, don't worry about it too much. It's just for the people who are comfortable there to help make it very clear what's going on. Right, so here's the data set. I've just copied it into Excel, and then I'm making the different distance matrices. Euclidean, Manhattan, max coordinate, min coordinate. Okay. Remember, a distance matrix is always going to be symmetric. So the lower triangle always looks like the upper triangle because A to B is the same as B to A, right? And all I'm calculating, this is a little bit harder to read, but essentially I'm looking up in the table up here. So take the value for Bill, look up Bill's values, right? Take Angela, look up Angela's values. And then we're taking the difference between these two, square it, the difference between these two, square it, the difference between these two, square it, add them all up, take the square root, that's Euclidean distance, and then spit the result out. Okay, so that's there. If you want to look at how you would do it in Excel, you can do it that way. You could do it by hand, or you could do it in R. So in R, it's here. Okay, so problem 2, I'm repeating the question here. I reiterate what min coordinate distance is. Remember, Euclidean is Pythagorean theorem, so finding the hypotenuse on the triangle. Manhattan distance is also known as taxicab distance. That's just adding up differences on each dimension, right? Because I can't go through a city block, I have to go around it. Max coordinate distance is take the difference on each dimension. Whichever one of those is biggest, the maximum, right? That's my distance. And then min coordinate distance is, again, take the difference on each dimension. Whichever one is smallest, the minimum, that's my distance. Okay, so I could use any of those 4 procedures to build a distance matrix and then find out who's most similar to one another based on having the smallest distance values. So here, I'm just reading the data. I created a data set and put it in a CSV file. It looks the same as the PDF matrix I showed you. Lab 3_2 is not there. One sec. Lab 3_2 is right here. Okay, and remember, it's giving me this warning just because the way the file was saved. There's some dangling commas in the comma delimited list. It's not a problem. It's just warning me that it had some empty values there. But here's the data again. So again, it looks the same as what's in the question. I just made a data frame with it. The first column are the people's names, like before. So I'm pulling those out for a second. And then I'm removing that column because I can't do distance calculations with a name.
So you always convert the data frame into a factor before doing the distance calculation?
Not as a factor, no.
Oh, okay.
Factors are for nominal variables. You need numerical continuous data to do distances.
What I understand with the data frame is like you have categorical and then numerical records, right?
Yeah, and distance calculations require numerical values.
Okay.
So you can't, there's no conceptually easy way to talk about what the distance between my name and your name, right? As opposed to I can calculate the distance between my height and your height would be very straightforward. So we're taking the names out. We'll use them later for labels, but we're taking them out for the time being to do the distance calculations. And again, I can use this dist function like I did before in the hierarchical clustering case to create the distance matrix. And I can tell it, use Euclidean distance, use Manhattan distance, use max coordinate distance. There's actually no option for min coordinate distance. So you'd have to do that one yourself. Okay, but I'm just recalling the dist function with this data frame of values and saying use different distance metrics. Upper equals true means don't just calculate the lower triangle, also fill in the upper triangle, even though it's redundant because the values are symmetrical. Okay, and then store the results in this variable. Now what it gives me back here right? This is the distance matrix in Euclidean distance. It's much faster than doing it by hand or in Excel, obviously. Okay, I'm converting it from a data frame to a matrix. This is not super important for the moment, but it's just when I want to add names and stuff back in, I can't have a matrix anymore. I need to have a proper sort of spreadsheet to work with. So I don't know why I'm doing this actually. And I think this is actually unnecessary, that I don't need these matrices. So Manhattan distance, max coordinate distance. I'm then putting the column names and row names back. Okay, again, instead of using 1, 2, 3, 4, I'm putting back in Angela, Bill, Tom, okay? T, this function is short for transpose, right? So essentially transpose, if you have a vector, it takes it from being a column and makes it a row, or vice versa, okay? So the only reason I'm doing that is because it expects, so what's coming from the row names, it's not in the right format. It's either coming as a column and it expects it as a row, so I'm just moving it before I pass it the values.
Sorry, can you say it again? Like T is a transfer function, so it adapts to whatever I need.
Yeah, it expects the values to come in either as a vector or as a row of a list of values. So I'm saying transpose what's there to make it the right format, and then otherwise you'll get an error message. Because it'll say yeah, it'll say the dimensions are wrong. Instead of being 4 by 1, it's 1 by 4.
But by using the T function,
you transpose it. So instead of, you move it from being 1 by 4 to 4 by 1.
okay, so it takes care of it.
Yeah. Row names. Okay, so this is why I was converting to matrices before. So you do need to make those matrices. So I'm just adding the labels back, and then I can view each of these. Hey, there's my distance matrix for Euclidean distance, and there's my distance matrix for Manhattan distance. So if I'm looking at Manhattan distance and I want to say which two people are most similar to each other, who am I going to go with? Yeah, you can see it here.
Like David and Charlotte.
As David and Charlotte, right? Because they have the smallest Manhattan distance between them, 46. David is 46 from Charlotte in terms of that calculation. So they're the most similar to each other. Okay. Any questions about these distance calculations?
You're just showing us, but one question, like for example, for
And again, you don't have to do this in R. I'm just showing you how you could do this in R. Yeah.
and how when I look at the max coordinates table, like how can I understand that with regards to that?
It's the same idea. It's just recall max coordinate distance is, so if I go up to my problem here, right? Max coordinate between Angela and Bill, essentially I'm going to take their difference on exam 1, the absolute difference. I'll take the absolute difference on exam 2 and the absolute difference on exam 3. Okay, and the biggest one of those, that's their distance. Right, so 28, 40, 32. So 40 is the distance. Okay, it's just the absolute difference on each dimension. And you take the biggest one, the biggest
This
dimension.
one doesn't really tell us how similar they are.
It does. You're just being kind of conservative in some sense. So whatever dimension is farthest apart, that's the one I deem to say, like, now this determines how far apart you are.
So, but like if I look at the maximum coordinates, then I would look for the smallest value and say, okay, these two are closest to each other.
Yeah, so it's a little confusing. Essentially, you're calculating the maximum distance among all the dimensions for two people. That's the distance measure for them. And then the question is saying, find the value that's smallest. So which two people are closest together?
Exactly. So I would look at the smallest, like at
Smallest big difference, yeah.
Like
Yeah.
difference. But then it's not David and Charlotte anymore, right? If you look like
I
on
mean,
the
we can
particular
check,
R.
yeah, probably not. So max coordinate, we
Then
have a
would be Bill
tie
and
actually. Yeah. Bill and Angela and Charlotte and Bill are equidistant.
So
So-
why is that? Why do I get like these different?
Because they're calculated with different equations, right? So Manhattan distance is just adding up. So I calculate the absolute difference on each dimension, and then I add those three values up.
So that again would be subjective for me.
No, this is objective,
Yeah, because there has to be like one pair that is closest to each other.
unless you get a tie, as we did here.
Subjectively, the algorithm
It's your choice, yes. It's up to you what distance metric you use, but given a distance metric, I can objectively say which people were closest.
Exactly, but depending on how I choose my distance metric,
You'll get a different
that
answer.
will give me a different objective result, which then changes
What you conclude.
what I'm gonna say.
Yep, yep.
So what's your advice for this? Like, how can I be sure? Like in this, like it looks like such an easy example, like seeing like different people with different like exam results, and it kind of seems like an easy concept to say, okay, just tell me the two people who are closest with their exam results.
Well, it's up to you to kind of make a judge, sort of a educated argument about what the appropriate distance metric is for the people, depending on what it is you're trying to do.
So in a certain way, if I say like, okay, if I'm just looking at like all exams together, or if I'm looking at like different exams individually.
So the way I would order these distance metrics that I'm talking about here, I think min coordinate distance is the most liberal in some sense, in that you're saying two people are similar if they did similarly on any of the exams. Max coordinate distance is saying you're very different if you did very differently on any of the exams. Manhattan is saying if however differently you did on any exam, we're going to add all those differences up, and that's how different you are. Right? So it's like increasing in terms of how conservative you're being, but again, it depends on the question you're trying to answer.
And the Euclid distance?
Euclidean distance is almost like averaging across these things.
Okay, so that would in that sense like average to all the exams?
That one makes the most sense. That's why it's often the default
And
that all the
then
functions
exactly
use,
tell
because
you
it
on
uses like an
how
average.
close they are
Yeah.
with each other.
Yeah, it's kind of weighting across the different exams. How did you do compared to this other person?
Okay, so it was mathematically that would be the one that kind of
Yeah, and again, it will often be the default distance metric. Okay.
Okay.
Any other questions?
Oh yeah, I had another one actually. Like
Okay.
For like in the command max accord where you like put upper is equal to true, what is the upper?
So that's saying don't just calculate the distance matrix for the lower triangle, also fill it in for the upper triangle of the matrix, even though it's just symmetrical, it's just redundant.
Okay.
Yeah.
Just to make sure.
Just because when I draw it for you, you now see the measures are both there. Yeah. Yes?
So row names is saved as not as a matrix of 4 by 1 or 1 by 4, which is why you're transposing for both row names and column names.
Yeah, so if I say, yeah, so the dimensions, so dim is saying give me the dimensions of the thing I'm going to pass to you, right, in terms of rows and columns. The dimensions of the row names property of this matrix is a 1 by 4. So it's not a vector, it's a row of values.
So for column names, why are you transposing?
So column names, similarly, 1 by 4. So it's don't think of it as a part of the matrix. So it's not, you know, they're making the sequel. So anyway, it's not actually a part of the matrix. It's not another column. It's metadata. It's a characteristic of the matrix that's stored somewhere else entirely.
So we took the names out and we put it in something called row.
Right.
This is called names, right?
Yeah. So think about this. So row names is a vector. It's 4 by 1, always. These two things both expect a value that's 1 by 4. So I got to transpose it both times. Okay? Okay, we have a handful of minutes left here, so let me see what I can get through. So that's continuous distance measures. The next one is Jacquard distance. Okay, so it's the exact same thing, except now we're working with binary data. You can make a distance matrix, and you use Jacquard distance this time. When does it make sense to use Jacquard distance? What kind of binary data? Anybody remember? Remember, we can use matching distance. So why would we use Jacquard distance instead of matching distance?
Measure similarity.
Yeah, they're both measuring similarity. It's not symmetric binary data, it is asymmetric binary data. Remember the example in your head? Jacquard distance or asymmetric binary data, the good example to recall is it's kind of like when you're testing for something like a rare disease. If both people do not test positive, that's not really surprising to anybody, and we don't really think it's that informative. But if you both test positive, that's highly informative. As opposed to if we have red, green, and blue for a product, and two people are, you know, maybe we then assume if we're not both red, that's equally informative to if you are both red. Right? That's the difference between symmetric and asymmetric. The ones matching doesn't mean the same thing as the zeros matching. It's more informative when you see two ones together than if you see two zeros. Okay, thinking about like rare properties. That tends to be when you consider data to be asymmetric binary data. You use Jacquard distance when you have asymmetric binary data, when matched zeros are not informative because they're a rare characteristic. Okay? So in this case, we have people that have taken 4 tests. Right? You could imagine they're medical tests or something. And again, this is a situation where maybe we're saying that if we both have a 0, we expect most people in the population to have 0 because it's rare. So having both zeros doesn't make you similar. It makes you just part of the regular population. But having 2 1s means that is very informative. You're quite similar in that respect at least. So Jacquard distance, we could calculate for each pair of people and make a distance matrix, right? Just like with the other calculations we were doing. And recall, Jacquard distance is, here we've got 4 dimensions. So it's the proportion of dimensions where we had a mismatch, right? So it's, well, actually that's matching distance. So it's how many dimensions did we mismatch on, where one of us was a 1 and the other was a 0, divided by how many dimensions did we have where at least one of us was positive. So we're throwing away those dimensions where both of us were negative because we don't care about that. It's not informative. So in this case, Archie to Barbara, mismatch, 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 mismatch. So we have 4 divided by 4 dimensions where at least one person was positive, so our Jacquard distance is 1, which makes sense because they're different on every dimension. Right? The maximal value is 1. Conversely, or alternatively, Barbara versus Charles, we have 1 mismatch on test 1, and then again on test 3 and test 4, so that's 3. And how many dimensions where at least one person was positive? 4. So 3 out of 4, 0.75 is their Jacquard distance. And essentially we're saying they're more similar than Archie and Barbara because they were both positive on test 2, which we deem to be an informative thing that's implying similarity.
But then the closer we get to 0, the more similar those people become.
No, the closer we get to 0, the fewer mismatches we have. Remember, this is a distance metric, not a similarity metric. Yeah. Yeah.
Which means that they become more similar because there are fewer
As you get closer to 0, you're more similar to each other. Yeah. Bigger value, you're farther apart. More mismatches out of cases where at least one person was true. Okay, so you could calculate a distance matrix in the same way we did before using that measure. And again, that equation's in the slides if you want to refer back to it. I have the solution here in case you're curious. Okay, so all I did was go through for each pair of people. I calculated their Jacquard distance metric. Okay, and we want the people who are most similar, so the smallest Jacquard distance value, as well as the pair that are most farther apart. So these people are farthest apart because the Jacquard distance metric is highest, Archie and Barbara. They were different on every dimension. And then these people were most similar, Archie and Charles, because their Jacquard distance was 0.33. So 1 out of 3 cases were they different, where at least one person was positive. Yes?
I don't understand from where you're getting the 2 4s.
The 2 4s. So Archie and Barbara?
Yeah, like because I have 1, then 0, 0, and then 1.
Yeah, so again, this is the difference on each dimension between these 2 people. So numerator is the count of cases where the first person was a 0 and the second one was a 1, plus the cases where the first person was a 1 and the second person was a 0, i.e. number of dimensions where we didn't match, but at least one of us was positive. That's all 4 of these, right? Mismatch,
Because they
mismatch,
have
mismatch,
different
mismatch.
Numbers between Archie and Barbara.
Yeah.
Okay, like all the tests were different.
Yeah,
between them.
they don't match each other on any of these 4.
Okay.
So it's 4, and the denominator is how many dimensions where at least one person was positive. That's all 4. Okay, so of the cases where at least somebody came back positive, we're different on all of those.
And why the other day when we were looking at the tests, we saw as the target variable true or false? Is that related with Jacquard distance?
I don't remember, I'm not sure what you're referring to.
False and true instead of like a 1 or 0. Instead of
So
like
true, I mean, binary 1 and 0 can be converted into a logical format of true and false.
okay,
But that's nothing specific to Jacquard.
Okay.
That's a general idea. Yeah, that's a Boolean value, true or false. Yeah. Okay, the last question was saying, imagine you have 10 stores in a city and you have 2 warehouses you want to build. You have money for 2 warehouses to distribute products, right? Where should you situate those warehouses? So essentially what I'm doing is taking latitude and longitude for the different addresses in my data set, and then I'm doing a clustering solution with k equals 2. Now, in practice, I would probably want to do something that accounts for like road travel distance, not direct line of sight.
So Manhattan is,
Yeah, well, even here, it's not in New York City, so Manhattan won't even be great, but that would be better. Yeah. So there's a few concepts. There's code in here that we're out of time, so I can't run it. You don't need to know it. It's totally demonstrative about how you could go through this process of geocoding addresses and then clustering on those latitudes and longitudes to figure out where should I put my warehouse. That's in there. It has some problems, right? There's some assumptions in there that you could think about. But the solution notes basically say, there's a few concepts you need to make reference to here or understand. So number one is this idea of translation. So recall that if I have a bunch of addresses, I can't just calculate distances on character values. So I need to convert it into some other format, in this case, latitude and longitude. So that's the idea of translation, okay? Once I get the GPS coordinates, right, latitude and longitude, now I can substitute those things in, right, based on geocode using an API, like Google Maps API. I use the R Data Science Toolkit here. So the code's there and shows you how you would geocode addresses. I then map them for you just because that's why not. I show you where in Texas they are. And then you can calculate geodesic distance in kilometers, for instance, between these latitudes and longitudes. Okay, I'm just going to use Euclidean distance here. That's not strictly correct in practice. Distances that are locations farther apart in the globe, you're supposed to use Vicente distance, which accounts for the curvature of the Earth and stuff. Don't worry about it. Okay. Once I have that data, then I can just come up with my k equals 2 clustering solution on those addresses, right? And the resulting latitude and longitude of the centroids, that might be where I'd put my warehouses, right, to be central for all those stores. Okay, so I have the code in R. This was a conceptual question where I just wanted you to like write out what you would do. Okay.
Why don't we use Manhattan or like any distance measurement that accounts for actually like the street distance that has to be.
You probably could, and actually I think Google Maps API will give you the distance between 2 points in terms of road travel.
Yeah.
I didn't get that because I didn't. They make you get a developer API and then you have to pay for more queries and stuff.
Up with this, okay.
So I didn't want to do that. It used to be free. It's not anymore. That would make sense, unless you're using drone delivery or something, then you can just fly. Yeah. Okay. Okay. Any questions about this? This was a purely written conceptual question.
But okay. So we don't have to like solve this for the assignment, for example.
No. But I've given you code in case you have a situation with logistics and stuff in a future job or something where you wanted to do this.
Yeah. Just
Okay.
avoid.
Okay.
Just in case you want to check out what.
It's just for your interest only. Yeah.